Hi, welcome to my channel JaberTime. Here's another problem about the kernel. This one is from r to the third to r to the second with the matrix of transformation given right here, 2 by 3. Notice that the 2 by 3 comes from this 2 and this 3. Find the kernel, the range, describe geometrically each, find the dimensions, and verify that the general Rank-Nullity theorem applies. Let's get started. One more time, here's the problem. And now we need to define or talk about the kernel to get started. Then we'll jump to the range. The kernel will be all the vectors in r to the third, which is v, that will be taking me under the transformation to the 0 vector in r to the second. Differently, we say ax equals 0, because that's how we define the transformation with the matrix A. Writing this as augmented matrix without writing the equal signs and writing another matrix with x's and equal sign and zeros on the right side, we call it augmented matrix. So that is exactly ax equals 0 without saying equal and so on. This one is ready to reduce the matrix to reduced row echelon form. So we need to target the -3 and make it 0. Making it 0, we use row operations, and we're going to multiply the first row by 3 to bring the opposite of -3 and add it to the second row. Differently speaking, we say we're going to multiply the first row by 3, go to the second row and add the result and keep it in the second row. That's how we write it down. I like these arrows and kind of like it shows exactly what we're doing. So we have 1, 2, 3, 4. We're going to apply the first element, second element, third, and fourth, and show that right here. 3 times 1 is 3. Added to -3 will be 0. 3 times -1, that's -3, added to 3 will be also 0. 3 times 2, which is +6, added to -6 will be also 0. And the last column, nothing's going to happen. It's going to stay 0. 3 times 0 plus 0 is 0. Well, at first we did not maybe pay attention or see that the second row is a multiple of the first row. So it's a duplicate. But that shows that the second row is dependent of the first row. So we could eliminate it. So that's what we have. We have zeros all over the second row. So we're done. That's called reduced row echelon form. There is nothing else we could do. What does that mean? It means that 1x1 minus 1x2 plus 2x3 equals 0. One way to simplify and see the answer to this solution, I mean the solution for the ax equals 0, is to write x1 by itself. That's one option. We could write x2 by itself. Why would you pick x2? I don't know, it's the same thing. So x1 becomes positive x2 after we move it, and negative 2x3 on the other side. Alright, so now we have two free variables. So if I know x2 and I know x3, I'll find x1. So let's call x3 A, and we'll call x2 B. So this simplifies to this look. x1 is b minus 2a. We're almost done with the kernel. So the kernel of t is all the x's in r to the third such that they take a look of this format. They look like x1, which is b minus 2a, where x3 is a and x2 is b. We have two free variables. That's my a and b in our real numbers. Sorry for that noise. Moving on. So now, to simplify this even further so we could read the basis for the kernel and identify the dimension, I need to separate this, focusing on b and a as scalars, let's say. Here we go. So writing the b's only without a's, it's b here and b here and no b's here, so 0. Writing it with a's only, that's going to be minus 2a, that's going to be 0a, and that's going to be 1a. Now pulling b outside as a common factor, pulling a outside as a common factor, or a scalar, it's going to be called. We have b times 1 and 1 and 0. We have a times negative 2 and 0 and 1. So that's called linear combination of linearly independent vectors. That's how the kernel is being described. Geometrically, this describes the plane through the origin in r to the third. Because we are in r to the third, we have vectors with 3 components, which is spanned by the linearly independent vectors 1, 1, 0 and negative 2, 0, 1. So what's the dimension of the kernel? Since I have 2 independent vectors, it's 2. To graph it, to show you how it looks like, I did that on GeoGebra by typing a and b and c as the origin. The plane that contains a, b, c is graphed right here. Here's c, 0, 0, 0 at the origin. As you could see, we're going back, and we could see that this point right there, which is 1, 1, 0. Okay? It's on the plane being shaded 0 for z. So it's right there, 45-degree in the middle of x axis and y axis, positive x and positive y. This point is back to negative 2 in the back of x axis, and it has 0 for y. It's not moving right, if you call it that way, or left, and it's lifted up 1 unit for the z component. So that's one view. I could just move it around and show you different angles, but you could just type this in GeoGebra if you like GeoGebra, and you'll see it. It's kind of a neat software that's free. Alright, now let's talk about the range. For the given transformation, the range will be the call space A. And there's more details about what's called space and so on in my other videos, which you could visit, and I'll try to link them down below in the description. For the reduced original form of A, we see that a basis for the call space is given by the first column only. Why? Well, that's the reduced original form, and that's the only pivot element that we have. We don't have 1 here and 0 here to consider this another column, so it's only the first column, and we take it from the corresponding vector in the matrix A. So that's this one right here. That says that the range of T, the transformation T, is all the vectors in R to the second, such that they are scalar multiples of this vector 1, negative 3. So the basis is just one vector, which is 1, negative 3. What does that mean geometrically? Well, if you're going to go through the point in the xy plane, because we are in second degree or two-dimensional plane to go to 1, -3. Of course, as a vector, we're going to go through the 0. This is the line through the origin that goes through 1, -3 or spanned by the vector 1, -3. What's the dimension? One vector only, so it's 1. The dimension of the range is 1. Let me show you the graph of the range in 2 dimension in r to the second. This is my vector in the basis. So I typed 0, 0, I typed 1, -3, and I went to the line between A and B. The software wrote for me y equals -3x. This line is y equals -3x. Slope of -3, go down -3 over 1, and the y-intercept is 0, so it's just -3x. Of course, by connecting this point and this point, you could see rise and run and write the equation yourself, but the software does that for us. All right, now let's go back to the problem. So what we have, we're going from r to the third to r to the second, defined by tx equals ax, that linear transformation with the matrix of transformation A, and that's my A. I mentioned it's 2 by 3, and that's where the 2 comes from and the 3 comes from. It's not a 3 by 2, it's a 2 by 3. I showed more details why is that in my other videos. Moving forward, we started with the augmented matrix with row echelon operations. We came up with this right here. That's a reduced row echelon form, which translates to 1x1 minus 1x2 plus 2x3 equals 0, as you could see right here. And the kernel came up to be, after defining 2 free variables, the following. We pulled B out and A out, and we said the kernel has a dimension of 2 vectors because that's 2 linearly independent vectors, and we have a linear combination of 2 linearly independent vectors that satisfies ax equals 0. All right, range. Range, we looked at the reduced solution form, and we take the corresponding vectors from A that corresponds to the vectors that they have the pivot element 1, which is just one vector, 1, -3, and the dimension was 1. Now the theorem that we need to verify, the general-nullity theorem, says the dimension of kernel plus the dimension of the range should equal the dimension of V. That's a 2 right there. That's a 1 from the range, and we know V is this right here. That's my V, that's my W. So V is r to the third, which has a size of 3. The dimension is 3. 2 plus 1 adds up to 3, and that should do it. So hopefully that's not a lengthy video. I'll try my best with clear notes to show you everything, so you could go back and refer to it as lecture notes instead of writing on the whiteboard. Of course I could do this on the whiteboard, but it's not gonna take 12 to 30 minutes, 40 minutes. It's gonna take way more. Hopefully you like it. Thank you, and I'll see you in the next one. Thank you. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.